I am on the faculty of the University of California at San Francisco in the Department of Hematology and Oncology. And I'm going to talk to you today about what I study. I study cancer, and I study cancer in many aspects of it. And I approach this as a software engineer approaches difficult problems. We need spend a lot of time to understand many interesting things. But this is my encore career. I was vice president of software tools at Apple. Steve Jobs hired me to help with the Intel transition, to develop Xcode and the beginnings of iOS and the many wonderful platform technologies that everybody uses today. And I was struck at the time when Steve developed cancer that this was a tools problem. This is a problem that we lack the tools to sufficiently understand. But I didn't have the background yet to do it. So I returned to college and actually got my Ph.D. in bioinformatics and biomolecular engineering at the age of 48. And so, thank you. You can teach an old dog new tricks. Steve, as any patient does, has to make decisions through this maze of interlocking problems. Are you going to go for surgery? Are you going to have chemotherapy? Will you try radiation therapy? If those don't work, do you go for experimental therapies? Do you go into a clinical trial? Or do you try alternative therapies? And the tools for looking at these problems and choosing which is the right choice for you is very difficult. And even physicians really don't have tremendous guidance on this, except in a few special cases. Sometimes we really have to just study and understand and hope for the best. And I feel like that's a place where the medical world needs to improve. If we actually look at the statistics of who lives and how long they survive, we find that, in fact, one of the biggest issues is how quickly you're diagnosed with cancer and how quickly are you treated. And there's this enormous gap between patients in their 5-year survival rate, if they get diagnosed early and the cancer is localized, or they're diagnosed late and the cancer is spread throughout their bodies and suffer through. And this is not just a matter of the amount of cancer it is also the complexity of cancer. And I'm going to tell you about how cancer, like other things, are mutations that follow evolution. Nothing in biology makes any sense unless you understand evolution. But if you think about it through evolution eyes and the lens of that idea, you find that, in fact, everything makes sense. So you begin life with a few mutations, a few alterations in your genes that can cause cancer. Sometimes this is enough to cause cancer in a child. But most of the time, we have 3 billion A's, C's, T's, and G's in our body, and we accumulate these mutations, and they're mostly benign. We get them from radiation, we get them from the foods we drink, we get them from viruses and other things. And those mutations eventually catch one that we call a driver mutation. It drives the cancer, propels it forward, and increases the growth rate dramatically. When those driver mutations happen, among the things that get broken are the error-checking code that checks the DNA itself. And that error-checking process then begins this radical changes to the DNA. You can actually lose chromosomes, you can get multiple copies, you can get many, many more mutations. And what is happening is you actually don't have one cancer, you have many. You have a whole spectrum of them. And your immune system is working to kill them. But over time, it overwhelms the immune system, and of course you succumb. The notion of metastases, of course, is cancer that has followed this fitness curve and has found many niches in the body to live in. So you may start off with one kind of cancer in one location of the body, but it has found other places to call home. Cancer essentially has all the source code for every program your body has ever run, including the programs that will run when you were a fetus and ran during development. And those programs, is just punching it randomly, eventually finds one that is able to overcome the body's natural defenses. This problem feels to me a lot like a software problem, where it is running amok. And so one of the great technologies that we've developed in the last 10 years is targeted therapy. And so treating some cancers is a lot like debugging. You find the bug and you go after it. So for melanoma patients who have the BRAF V600 mutation, we use a drug called verafenib, and it goes and finds the cancer cells that have this specific mutation and blocks it and helps the immune system target that. Unfortunately, it's not like debugging, because the bugs actually adapt. That what happens along the way is we haven't killed all of the cancer cells, sort of like trying to kill all the mosquitoes with DDT. You'll find that there are a few naturally that are resistant to it, and those are the ones that grow and replace. Now you've got a cancer that is resistant to the drug that you used. This idea is that cancer can actually develop these many mechanisms of drug resistance, that those drugs that it can actually avoid the location where the drug was targeting. It can actually become a supercell where it actually kicks out the poison faster than it can take it in. It actually reduces the intake of the poison, and it can actually, one of the main mechanisms that we often use to fight cancer is we target damaging the DNA. Because cancer cells are some of the most rapidly growing cells in the body, we often target that. But in fact, cancer fights us on that, in some sense, by improving and being better at fixing the damage from DNA. And that, in fact, can cause even worsen the condition. So with all these problems, how do we understand what goes on? I'm going to talk to you now about a child named Quincy, who came to UCSF for treatment. And his mother noticed that just something wasn't right. He was 5 months old, and was admitted with an unusual rash and difficulty breathing, had a high temperature, he had discomfort, and had a very elevated white blood cell count, usually the sign of an infection, but it can also be, of course, a sign of cancer. Two pediatric oncologists that I work with, Minion Lowe and Dr. Elliot Stieglitz, saw Quincy and came up with, and immediately thought this might be leukemia. But the question is, which leukemia and how do you treat it? And kids do very well with leukemia treatment on the whole. But Quincy's cancer didn't respond. Over time, he developed this massive abdomen. And the diagnosis after some examination was that he had juvenile myelomonocytic leukemia, a rare but very usually fatal cancer. And the usual therapy for these kinds of leukemia is to ablate, to destroy all the bone marrow, all the blood-producing cells in the body, and give a cell transplant from a relative or very close match. But Quincy was much too sick for that. Quincy, would not be able to survive such a dramatic treatment. The chemotherapies were tried, and we went through one after another, and they showed no progress. Then we pull out our next set of tools, and that is to look at the genes themselves. So we sequence genes, Quincy's genes, using a panel we developed at UCSF called the UCSF 500 gene panel. And what we found was that there was a gene fusion, a connection between one gene and another that doesn't belong there. That this gene fusion actually puts in the middle this other gene, right square in the middle. And this kind of alteration, typically not something we're born with, but can happen randomly at any time because the splicing of the DNA can happen easily. And that's sort of like the idea of you have a headset, but instead of plugging in the right place in your stereo or your phone, you're actually plugging into the power supply. You're going to get this tremendous boost of signal that is just noise and causes this rapid growth. It's the wrong thing to happen. In trying to understand these kinds of phenomena, we're very fortunate that the federal government has created this Cancer Genome Atlas, TCGA, kind of a play on the A, G, C, and T's that we use. And this is a project that was just finished. It was a follow-on project to the Human Genome Sequencing Project. In that process, we've sequenced 15,000 patients. I did some of the analysis of this. It was really amazing because you get to see these patterns that recur and understand how cancer affects in multiple parts of the body. That we'll see the same mutations occurring in different locations, but causing almost the same cancer, but very different effect. And so one of the things we developed at UC Santa Cruz, where I was at the time, was this Tumor Map, a map where we took literally the Google Maps technology, and instead of it presenting the tiles of locations of places on the planet, we've had locations in this vast space of the cancer. And it allows us to zoom in. You can Google it and find it yourself. And what's interesting about it is we can then do an analysis of where an individual patient is by seeing how they correlate with all the patients on the map and to see where do they fit best. And we found Quincy. Quincy was between blood cancer, the leukemia, and kidney cancer. And that, of course, gives us the ideas that, in fact, that maybe therapies for kidney cancer might actually help treat Quincy. So there is, in fact, drugs that do that. And one very famous and important drug called sorafenib is targeted specifically for FLT3 gene fusions. And it's for treating very advanced kidney cancers. Oddly enough, it happened to be developed by Professor Frank McCormick, also at UC San Francisco. So we went and talked to him and found out more about this drug. We also did a literature search to see if this has ever been tried before. But in fact, when it has been tried before, it hasn't worked. Very much experimental, very much not necessarily the standard of care. Now we're looking into individual ideas of how to pursue things. And in fact, it was recommended not to try this on pediatric cancer patients. So with that in mind, though, we really were out of options. And at that point in time, we said, we have to try this, if not, to see if it will work. And so here's Quincy's white blood cell count. And it had climbed from the point in time that he started being seen up to very seriously dangerous results. And first administration of sorafenib worked to dramatically reduce. We said, okay, let's give him a little bit more, up to 200 milligrams, and even better results. And finally, at about 300 milligrams, amazingly, we saw him returning to normal, feeling much better. And in fact, we'll show a little bit.
9. What comes after 9? 10. To know that your child could potentially die from this process was just gut-wrenching. I mean, I just would go into the bathroom and pray and cry and just, please don't take my baby. It was really an emotional time for us. And this medication actually put Quincy into remission even before his transplant. So it was basically a miracle.
So this is Quincy. All credit belongs to his doctors. I mean, as a researcher, I'm just merely helping out this amazing process. So what's exciting about this is that we did have a curative treatment for Quincy, and these amazing targeted therapies helped. But we don't have this for every patient. And so part of the idea is, of course, that we need to figure out is how do we take this kind of precision medicine where we know an enormous amount about individual patients and how to treat them and give it for everybody? How do we scale up? In Silicon Valley, of course, this is a big part of this. And so one technology that I will talk about just very briefly is to introduce you to this idea of programming immune cells. And this is something which we've begun to do. We have immunotherapies that externally tell the immune cells to ignore the signals that cancer generates to say, don't eat me. And that's an amazing thing. We can block the ways that cancer evolves to avoid the immune system, to better tackle it. But I believe that a better technology is coming along. We have seen the first of these in actually putting genes into patients' immune cells. And someday, perhaps even making a generic immune cell that can be used for many, many patients. And the idea, of course, is that with this additional programming, a researcher, a doctor can work to improve and to turn your immune system to precisely focus and target your cancer. Perhaps even going beyond cancer into other diseases, such as Crohn's disease and other autoimmune diseases. So very exciting idea. In the meantime, what should you do? Well, life is, of course, a risky business. And it's extremely important that you avoid things that increase those risks. Really, it's just a probability game. You should avoid smoking of any kind. But if you need to smoke, smoke less. Oddly enough, obesity is very much a cancer agent. And we see much worse outcomes with patients who are obese. There are other pathogens in the environment, various kinds of viruses, unprotected sex can transmit those things that can cause and lead to cancer. And then there's a host of other dietary factors and being sedentary and other things that you have heard about before. Extremely important that you manage your risks. So this gives you some idea about what's going on. So what's the conclusion to this? Number one, avoid risky business. Seek treatment early before cancer has had a chance to spread. And be lucky enough to get a mutation that we actually know how to fix. And by the way, increase your luck by donating to cancer research. Thank you very much.